Okay, guys, more thermochemistry. Here we go. So I just want to recall when last we left you, we were talking about generically energy, work, heat, etc. W, Q, right? I just want you to recall that work requires a coherent or concerted motion of particles. There's got to be movement there in the system. Remember, things like expansion and contraction are happening. And if the system does not expand, then no work is done. So if the volume doesn't change, if we do not have a change in volume, if there is no delta V, this whole expression goes, this right here, this P delta V goes to 0. So in terms of, or we're going to talk about delta H in just a minute, but in terms of delta E, if we have that P delta V going to 0, then no work is done. Problem is that that's not true in most cases. In most cases, there's some sort of movement or motion of particles going on. There's some sort of even a slight expansion or contraction in the volume, and therefore, in most cases, work is done either onto or by the system. So you'll remember we talked so far about delta E equals Q plus W. Well, now we're going to talk about delta E in terms of delta H, or enthalpy. Enthalpy is very similar to delta E. There's a marked distinct difference, but you're going to find that delta E and delta H values for a particular chemical reaction are very, very similar. The real true difference between delta H and delta E is that delta E takes into consideration the energy of all work and heat that is occurring with a system and a surroundings, where delta H is only looking at a heat exchange and doing so under constant pressure. So we can look at this as enthalpy change, where we're relating Q with a subscript P, as in Peter, to indicate to us that we're talking about constant pressure. And what that's going to equal is delta E plus P delta V. This is what we talk about as far as enthalpy change or heat of a reaction. Now, because all the other things we talked about being a state function, for example, when we talked about energy and pressure and volume all being state functions. Remember, state function means it doesn't matter the route at which something goes from point A to point B. The route getting there is irrelevant. The fact that they go from point A to point B is what matters. So energy, pressure, and volume, they're all state functions. And because they are all state functions, enthalpy by definition must be state function because it uses energy, pressure, and volume. So one of the things you're going to see that we're going to see a lot of, generically when we talk about delta H, we're going to talk about it in terms of H final minus H initial, or the final minus the initial, or what that really means for us is the summation of the products minus the reactants. So if we look at this particular example here, this is a very, very common example. What you'll see is that delta H is negative here. It's negative 852. A negative delta H tells you that the reaction is exothermic. And what I want you to think of when you think of something being exo or endothermic is think of the word heat as an actual product or reactant. So if it's exothermic, heat is given off, and we would think of heat being on the product side over here. So this particular exothermic reaction means that heat is going from the system into the surroundings. It's being given off, exothermic. This is an example where we have an endothermic reaction. How do I know that? Because we have a positive delta H. A positive delta H indicates that heat needed to go into the system. So we would think of heat in this case on our reactant side. This is going to become important when we talk about Le Chatelier. If I look at these two things, these two equations, that we just saw this, this first one, this exothermic one, on the previous slide. See, it's this first one here. Now we're going to look at the same exact equation in terms of the forward and the reverse reaction. So what you're seeing at this top one is the forward reaction is exothermic. Okay, there's heat evolved or given off from the formation of iron, solid iron, and aluminum oxide. If I talk about the reverse reaction, or going back to the products, right, I just flip it. Now we have a very large delta H, but you'll note numerically the values are the same, signs are different. Okay, even though we flip this and we put it here, it's still endothermic because remember we said we think of heat, for example, like a product in this first one. We would actually write 2FeS plus Al2O3S plus heat. If we flip that, we're still saying plus heat, Fe, Al2O3. Heat is on the reactant side in this case, meaning it's endothermic. Heat had to go into the system to make the reaction go. Now, highly, huge, big number, endothermic, and took a lot of energy. So the same amount of energy, same amount of heat given off is equal to the same amount of heat used. So if we look at this, the question is how much heat is evolved in the complete combustion of 13.2 kilograms of propane? C3H8 is propane. Well, what they told you is that delta H of C3H8 is negative 244 kilojoules per mole. How do I know that? There's a chart in the back of your book. You will always be given a chart of the delta H's. You do not have to memorize any of them, save for water. Okay? So there's a chart in the back of your book. It's about 10 pages long of every delta H, delta S, delta G, everything you can think of for any gas you can think of. Now you need to be careful because the state of the element determines which delta H you'll use on the chart. So all of these elements have a delta H in the, well, not all, let's say 90% of them have a delta H, for example, for both the liquid, gas, and solid forms. Now, the molar mass for propane is 44 grams per mole. How do we know that? We looked on the periodic table, we added up 3 carbons and 8 hydrogens. So if I convert 3.2 kilograms to grams, now a simple division here gives us what? What is a simple division going to give us? Well, if you think about it, we're converting kilograms to grams and then use the molar mass. Okay? It's going to give us a number of moles. So Q is equal to 13,200 divided by 44 times the delta H for propane. That's how many kilojoules we're getting. Now you try. How much heat is evolved when 0.483 gram diamond is burned? The delta H of combustion for a diamond is negative 395.4 kilojoules per mole. Now, note, it's negative. So is this an endo or exothermic reaction? It's exo. How do I know? 1, it's a negative sign. 2, it says heat evolved. Heat evolved means given out, given off, put into the system. Into the surroundings from the system. So pause it, take a second, see if you can work this one out. Yes, we will do more of these problems in class. So the mole of one diamond, they told you the grams. Here's the grams. Divided by 12. This is a hugely rounded number. 12.011 is the molar mass of carbon. Carbon is what diamonds are based in, yeah? Total heat, Q, is equal to the delta H of combustion times the moles, the number of moles present, and it's a negative 15.9 kilojoules. So I just want to clarify one thing. When we give you the delta H of any compound, gas, liquid, solid, what have you, it is the delta H of 1 mole of that thing. So we got to figure out how many moles are in 0.483 grams or in 13.2 kilograms in order to figure out the total heat evolved. Okay, we have to take into consideration the number of moles and the amount per mole that that particular element or compound uses or needs. We're going to wait to do one like this in class together. I'm going to kind of skip this right now. All right, so when we're measuring delta H, the main way we can talk about this is in terms of calorimetry. And calorimetry is considered at constant pressure. Your assumed constant pressure. In fact, when you do this reaction, this lab in Chem 2, you're going to be using the pressure that's in the classroom based on our barometer that we have in there. We can read the pressure of the classroom. So just like everything else we've been doing, we can see that we have Q of the reaction equals the negative Q of the solution. Likewise, we can say negative mass of the solution times the specific heat of the solution times delta T. Okay, this is the one that we started to do and work on in class on Thursday, and that we're going to pick up with on Tuesday. So I'm actually going to I'm going to talk about that one as we're working through the problem. Okay, just understand that when we're talking about a calorimeter and adding, for example, cold water to hot water or a hot metal to cold water or what have you, this is relatively the setup we'll be thinking of in our heads. So we have a lot of relationships that are involved in delta H of reaction. So first of all, delta H of an entire reaction is the delta H of the products minus the delta H of the reactants. And we have to consider that if there's a multiplier in there or a coefficient used to say balance a chemical equation, that delta H must be multiplied by that coefficient also. So, for example, if you have C plus O2 yields CO2, and I tell you the delta H is negative 393.5 kilojoules for that, if there was a 2 coefficient in front of everything, then there'd be a 2 multiplied by that whole thing. Likewise, if I'm looking at a balanced chemical reaction and I look up the delta H for each individual, let's say I had to look up the delta H for this, delta H for this, the delta H for this, and I did my products minus the reactants, all of my individual delta H's for my individual elements would have to, if there was a coefficient in front of it because it was a balanced chemical equation, then I would have to multiply each individual delta H by that individual's coefficient. So for example, if delta H for CO2 was negative 293, and let's just pretend there was a 3 in front of the CO2, it would be 3 times negative 293 or whatever number I just made up. Okay. If the reaction is a reversed reaction, we reverse the sign of delta H. So you'll see here it goes from C plus O2 plus CO2. Well, this is the reverse. This is CO2 yields C plus O2. You'll note that, again, the number is the same. It's the sign that changes because we go from an exo to endothermic reaction if we're talking about the reverse reaction. So Hess's law. Hess's law states that temperature and pressure directly affect the solubility of a gas. Hess's law can also be related to delta H. So if we talk about this in terms of if a reaction is stepwise. Many reactions are stepwise. What that means is the first reaction creates intermediates as a product, and in the second step, the intermediates are used, the second step intermediates are used up as reactants in the third step. Okay. So if we can express, a series of steps for a particular reaction, then the delta H for the overall reaction is the sum of all the heats of reactions for each individual step. I'm going to say that again. So if I have 2 or 3 steps that are involved for getting from the total reactants to the total end products, and let's say there's 3 or 4 steps, the heat of reaction for each step involved, they would be added together to find the overall delta H of reaction. Yes, we're going to do examples like this too. So again, the only real difference between delta H and delta E, big picture, is that delta E takes into account the heat and work of all energy between the system and the surroundings, where delta H is only looking at the heat exchange under constant pressure. So what this says here, lighters are fueled by butane. When 1 mole of butane burns at constant pressure, it produces 2,658 kilojoules and does 3 kilojoules of work. So 1 mole of butane burns at constant pressure, should tell you delta H. It produces 2,658 kilojoules of heat and does 3 kilojoules of work. What are the values of delta H and delta E for the combustion of 1 mole of butane? Well, let's start with delta H and delta E and what they mean. So delta H represents heat exchange. So delta H, we know it's exothermic because we're talking about butane burning, right? So we know that delta H is negative 2,658 kilojoules. Good to go. And we know that is it because it's under constant pressure. Delta H is equal to Q subscript P when under constant pressure. Delta H is equal to Q subscript P, which means it's under constant pressure. Okay? Delta E, we have taken into consideration both heat and work. So remember, when we talked about delta E and Q and W, when we were deciding, well, gosh, is Q positive, is Q negative, is W positive, is W negative? All right, well, when heat is lost from the system, exothermic, Q is negative. That's where we're getting the negative 2,658 kilojoules. And when work is done by the system, it says it does 3 kilojoules of work. So the system is doing the work. We have a negative W also. So you'll note the difference here between delta H and delta E. It's only 3 kilojoules. Again, very, very similar in numerical value, but different because they take into consideration different things. We'll work on this, and we're going to actually do this particular example in class. So I'm going to skip on through it because there's lots of things I want to talk about with it. All right, so standard conditions. This is a really important concept. Standard conditions basically just means there's a standard state. It's a set condition, and it's defined by various things. We can really define standard conditions however we want, but there is a very specific temperature, pressure, etc. that it has to do with. So we're talking about 1 atm, 25 degrees Celsius, 1 molar concentration. Okay, so our standard state conditions are defined as 1 atm, 1 atmospheric pressure, 25 degrees Celsius or 298 Kelvin, and the concentration of 1 molar. Okay, the standard enthalpy change, we use a little naught, a little superscript naught. We call this H naught to represent that it is in standard conditions. So the standard enthalpy change, delta H naught, is the enthalpy change when all the reactants and products are in their standard state. So in order to have a delta H naught for the reaction, each reactant and products must also be in their standard states. So when we're talking about standard enthalpy of formation, the heat of formation, the heat required to form something, delta H F naught, it's the enthalpy change for the reaction when 1 mole of a compound, when 1 mole of a pure compound from its constituent elements are in also their standard states. So elements must be in their standard state, and the pure element in its standard state is equal to 0 kilojoules per mole. So if we have a pure element in a standard state, then the delta H of formation is 0. Okay, we kind of ignore those. So let me just see if I want to, give me 1 second, guys, I'm pausing. Okay, I'm sorry, I just had to fast forward through my slides a little bit. There's some stuff on here that I'm not holding you responsible for. I don't expect you to have to, predict how a chemical reaction comes about with the heat of formation, but if I give you a reaction, I expect you to be able to talk to me about it. I expect you to be able to answer questions about endo and exothermic, look on a chart and figure out, the heat of formation, the delta H of the reaction, et cetera, et cetera. So let me just see if there's, where'd did that chart go? Here it is. I just wanted to show you this really quickly. This is an example of what the table in the back of your book looks like. It's not table 6.5. This is completely from another textbook. But in the back of your textbook, you have, again, about 10 plus pages of heats of formation. And there are other things with that chart, the delta S, Gibbs free energy, etc. So here, this is what it would kind of look like. So if you'll note with bromine, there's bromine gas, bromine liquid, which is its elemental form, right? Br2, it's one of those diatomics. And then, for example, HBr. And it gives you the heat of formation for all three of those. You'll notice that Br2, although it appears to be in a compound, it is a diatomic, and that is its elemental state. So the heat of formation for that is 0. Regular calcium, solid calcium, that's its elemental state, 0. But the calcium oxide has a heat of formation of negative 634.9. So to form that, it's an exothermic reaction, okay? Silver all by itself, it's an element. Heat of formation 0. Silver chloride, negative 127. Okay. This is the stuff I'm not having any response for. Okay. So in order to calculate standard enthalpy change for a reaction, again, we're going to be talking about products minus reactants. So it's the summation of the delta H of formation for all of the products minus the summation of the delta H for all the reactants, taking into account any coefficients that might be present. I hate the way this looks. This is ridiculous. So let's just look at this. Oh. Okay. So if we look at this particular crazy chart, what we're looking at is CH4 plus O2 yields CO2 plus H2O. Okay. So enthalpy in this direction. First, they're talking about the decomposition. The decomposition of CH4 to O2 it's exothermic. Well, it's combustion, so we should know that anyway. But it's exothermic, meaning here are your reactants, here are your products. Okay? So to get from here to here, there's a net negative 802.5 kilojoules. Why? Because it's exothermic and because the energy of the products are lower than that of the energy of the reactants. Okay, so the first thing that happens is in step 1 of this reaction, this is a stepwise reaction. It takes more than one step to get from this to this. So step 1 is that CH4 degrades to graphite, solid graphite. Solid graphite is carbon in its elemental composition, and then hydrogen gas. So they've done the math for you. It's endothermic. Heat was put in to do this, and it's a decomposition. So we get a positive 74.6 kilojoules of energy into the system from the first step. Okay. From this step here, you'll note the graphite was produced as a product and used as a reactant in the second part, the second step. So here, graphite, it's produced and then used up with the oxygen gas and forms CO2. Okay, there's that. And then our hydrogen gas plus oxygen gas gives us our water. So our net would be used up, some of it, left over. Okay? So again, I'm going to walk you guys through one of these examples step by step by step by step. But when you're getting the heat of formation for all of these, the sum of all these, sorry guys. I don't know what I did. I hit the wrong way. The sum of all of these delta H's would be the delta H for this entire reaction. We'll go through these. Ignore the math for right now. Just have a basic understanding of how it works. So I just want to go over this really quickly. You'll notice that if I have delta H, ignore this down here. If I have delta H is the summation of the heat of formation of the products minus the reactants. So what that means is I'm going to add up the heat of formation for the carbon dioxide and the water, because those are the products, and I'm going to multiply water's heat of formation by 2, because there's a coefficient 2 in front of water. Then I'm going to subtract the summation of the reactants, so the heat of formation for CH4 and the heat of formation of O2, but I'm going to multiply that by 2 because there is a 2 coefficient on that O2. So if I go to the chart and I'll look these up, it's going to be negative 393.5 plus 2 times negative 241.8 kilojoules. Get that number, subtract from it this number, okay? 2 times 0, because oxygen gas is in its elemental form, okay? Oxygen gas is in its elemental form. So 2 times 0 is 0. So it's just this minus this. It's 802.5 kilojoules. And this is for the carbon, this is for the first step, okay? We're gonna do several of these in class next week. Okay. Okay, let's just talk about this one. The question is, how many kilograms of octane must be combusted to supply 1.1 times 10 to the 11 kilojoules of energy? Remember, combustion equations are always the same. It's the hydrocarbon plus plus oxygen gas yields carbon dioxide and water. That is always the set reaction for a combustion reaction. So we're going to have C8H18 plus O2 yields CO2 plus H2O. So the first thing you have to do to get the delta H, I wish I could write on my computer, guys, I can't. We're just going to take the summation. Well, first write and complete and balance the chemical reaction. You've got to do that. And once you've written, completed, and balanced the chemical reaction, you're going to take the products, add them together, taking into account any coefficients, subtract it by the reactants, taking into account any coefficients from the balanced chemical reaction. We'll do these in class. Phase change. When we talk about phase change, we need to talk about energy in terms of each step of the phase change. So every individual compound has its own boiling point and melting point. And so if I were to, let's just talk about water for a second. Water's melting point is 0 degrees Celsius. Its boiling point is 100 degrees Celsius. So if I were to take, 25 grams of water, and if I were to take it from, say, negative 10 degrees Celsius to 110 degrees Celsius, for each part of that phase change, I would have to take into account the amount of energy it takes. So I would have to take into account the amount of energy to get from negative 10 degrees to 0 degrees, the amount of energy to melt it, the amount of energy it takes to get from 0 degrees to 100 degrees, then the amount of energy to boil it and, evaporate it, and then the amount of energy it took to get from 100 degrees to 110 degrees, okay? So that would be like a 1, 2, 3, 4, 5, like a 5-step problem. And when we work on these problems, I'm going to draw it out for you. When you come into class on Tuesday, make sure you have a couple of pages that are large enough, or empty enough for this particular type of problem will take an entire page of notes. So what I'm going to do is I'm going to talk more about this as we go through this topic. I'm going to kind of teach it as I go. Okay. We're going to have 2 different kinds of reactions that we're dealing with this. The first type of reaction equation we're going to talk about is the heating or cooling down part, and then the state change equation. So there's an equation to figure out the energy as we're heating up or cooling down, and then there's an equation to figure out the heat as it changes states. Okay? We're not going to talk about global warming. Oh, that's cute. Okay, this is not your final exam. This is from another class. All right, guys, come to class on Tuesday. Be ready to do problems. Get your algebra thinking minds on. Don't let the fact that stuff looks weird throw you off. And we're going to work a lot of these problems now that we've lectured on it. And it may just make a whole lot more sense to you after we start working the problems. So what I suggest doing, now that you've watched this, what I suggest is after we leave class on Tuesday, go ahead and rewatch it with those examples in front of you. Okay?